So we'll be moving forward with tutorial 8. Additionally, I will also be available on Hangouts to take any of your doubts, and I will also be uploading a condensed version of these slides on Classroom. So these are the questions that we'll be going through today. You can note them down if you want. Alright, so let's start with the first question, which is quiz 4.10b. So the question says, random variables x1 and x2 are independent and identically distributed with probability density function fx of x equal to 1 minus x by 2 for x belonging to the interval 0 to 2 and 0 otherwise. And in the first part, we have to find what is the joint PDF f of x1, x2 of small x1, x2. And in the second part, we have to find the CDF of z is equal to max of x1, x2. So essentially, let's think about the first part here. So the joint PDF f of x1, x2. So we know that x1 and x2 are independent and identically distributed, right? So in that case, the joint PDF is simply the product of the individual PDFs. So which will be equal to basically f of x1, x2 will be equal to f of x1 into f of x2. So that will be equal to 1 minus x1 by 2 into 1 minus x2 by 2 for x1 belonging to 0 to 2 and x2 belonging to 0 to 2 and 0 otherwise. So I think that's clear enough. So for the next part, we have to find CDF of z is equal to max of x1, x2. So CDF for the cumulative distribution function denoted by capital F is basically capital Fz of z is equal to the probability that the random variable z assumes a value less than or equal to small z. So now I want you to take a minute to think about this. Essentially, how will you ensure that capital Z is less than equal to small z when we know that z is the max of x1 and x2? So essentially, if both x1 and x2 are less than equal to z, then the max of x1 and x2 will also be less than equal to z, right? So basically the CDF of z, fz of z, which is the probability that z is less than equal to small z, is same as the probability, the joint probability that x1 is less than equal to z and x2 is less than equal to z. So if both of them are less than equal to z, their maximum value, which could be either x1 or x2, would also be less than equal to z, right? So we also know that these are independent basically, and in that case their joint probability will be the product of their individual probabilities. So this will basically become probability that x1 is less than equal to z and probability that x2 is less than equal to z, and both these terms are basically nothing but the CDF of x. x1 and x2 are IID variables, right? So p of x1 less than equal to z is basically fx of z, and p of x2 less than equal to z is basically fx2 of z, and x1 and x2 are both equal to x, so that is basically the square of CDF of f of x. CDF, which is f of x, fx of z, right? So anyway, so basically to find out the final expression for CDF of z, we need to find the CDF of x, and what we have given in the question is basically the PDF of x, and to basically find the CDF, we will integrate the PDF over the interval minus infinity to infinity, which will basically become 0 to 2 since the function is 0 elsewhere. So basically fx of x is equal to fx of y dy integrated from minus infinity to x, and basically if x is less than 0, this term would be the term, the PDF term fx of y will be equal to 0, and for x belonging to 0 to 2, it would basically, the limits would basically change from 0 to x, and the term would basically become the integral of y minus half dy, limits 0 to x. So basically what we'll get over there is x minus x square by 4, and for x greater than 2, this will basically become 1. So now we have obtained the CDF of x, and we know that the CDF of z is basically the square of CDF of x. So now to write the CDF of z, we'll basically square each of these, the value of the CDF of x for each of these intervals. So for z less than 0, the CDF of z will be 0. For z belonging to 0 to 2, the CDF of z will be the square of this term, which will be z minus z square by 4 ka whole square. And for z greater than 2, it should be equal to 1. So essentially there is a typo here. It should be z greater than 2 instead of z greater than 1. Alright, so we have basically found the CDF of z as well. So let's move forward with the next question, which is example 4.20. And the question says, for random variables x and y in example 4.5, we found in example 4.19 that the conditional PDF of x given y is f of x given y is equal to f of x comma y divided by f of y. So what this basically says that the conditional PDF f of x given y is equal to the joint PDF f of x comma y divided by f of y, which is equal to 1 upon 1 minus y for x greater than equal to y and less than equal to 1 and 0 otherwise. And we have to find the conditional expected values e of x given y is equal to small y and e of x given y. So first I guess we'd like to understand what is the relationship between these two, and this definition can give us a better idea about that. So what this basically says is that the conditional expected value e of x given y is a function of a random variable y such that if capital Y is equal to small y, then e of x given y is equal to e of x given y is equal to small y. So what this basically means is the value e of x given y is equal to small y is basically the same as e of x given y at the value y is equal to small y, right? So let's move forward. So what we have to find is e of x given y is equal to small y, and basically the expectation, we'll be using the standard formula for expectation, which is basically x multiplied by the conditional PDF of x given y and integrated over all possible values of x. So this is essentially x f of x given y dx from minus infinity to infinity. And right, so f of x given y we were given as equal to be 1 upon 1 minus y for the values of x ranging from y to 1. So the integral that we have here is 1 upon 1 minus y into x dx integrated over the interval y to 1, and upon integrating this we'll get basically x square upon 2 divided by 1 minus y, and the limits are basically y to 1, and so the value that we get for this is basically 1 plus y by 2. So this, as we learned previously, is basically a special case of e of x given capital Y. And now to find e of x given capital Y, we'll just swap small y as capital Y. And since we know that e of x given y is equal to small y is just a special case of e of x given y. So now we have also obtained e of x given y. Right. So let's move forward with the next question, which is problem 4.9.3. And this says x and y have joint PDF f of x comma y is equal to x plus y for x and y greater than equal to 0 and less than equal to 1 and 0 otherwise. And for the first part, we have to find for which values of y is f of x given y defined and what is f of x given y. And for the second part, we have to find for which values of x is f of y given x defined and what is f of y given x. So we already know that the conditional PDF f of x given y will be equal to the joint PDF f of x comma y divided by f of y, and likewise f of y given x will be equal to the joint PDF f of x comma y divided by f of x, right? So this basically so now you have to find for which values of y is f of x given y defined. And I think it's pretty obvious that it will be defined only for the values of y for which the joint PDF is defined, right? And we know that the joint PDF is only defined for values of x and y belonging to the interval 0 to 1. So I hope that is immediately clear to everybody, right? So, right, for the first part, we have to find for which values of y is f of x given y defined, and what is f of x given y, given that the joint PDF is x plus y for x and y belonging to the interval 0 to 1. So the conditional PDF f of x given y is defined for all y such that y is greater than equal to 0 and less than equal to 1. And for y belonging to this interval, we will have f of x given y is equal to the joint PDF f of x comma y divided by f of y, which is basically, so we basically need to find the denominator over here, which is fy of y, and that will be equal to the joint PDF integrated over all possible values of x, right? So this term basically becomes the joint PDF, which is x plus y divided by x plus y integrated over all possible values of x, which basically reduces to the interval 0 to 1. And so finally what we get here is x plus y divided by x square by 2 plus xy, limits 0 to 1, which is basically 1 by 2 plus y. So yeah, what we have is basically x plus y divided by y plus half for y belonging to 0 to 1 and 0 otherwise. And similarly for the next part, we have to find for which values of x is f of y given x defined, and f of y given x will be defined for x belonging to 0 to 1, and again to find f of y given x, which will be equal to the combined PDF f of x comma y divided by f of x, and to find f of x we have to integrate the joint PDF over all possible values of y. So this is similar to the previous part. This is basically x plus y divided by x plus y dy over the interval 0 to 1, and the final answer also similar to the next part, similar to the previous part, comes out to be x plus y divided by x plus half for x belonging to the interval 0 to 1 and 0 otherwise. Over to the next question, which is problem 4.9.7, and this is a pretty lengthy question. So the question says the probability model for random variable a is PA of a is equal to 1 by 3 for a is equal to -1 and 2 by 3 for a is equal to 1 and 0 otherwise. So basically the random variable a assumes two values, which are -1 and 1, and their corresponding probabilities are given as 1 by 3 and 2 by 3. And the conditional probability model for random variable b given a is p of b given a, b given that a is equal to -1 is equal to 1 by 3 for b is equal to 0, 2 by 3 for b is equal to 1 and 0 otherwise. So what this says is that if a is equal to -1, then the probability distribution of b given a is 1 by 3 for b is equal to 0 and 2 by 3 for b is equal to 1. And the next part is p of b given a, b given a is equal to 1 is equal to 1 by 2 for b is equal to 0 and 1 by 2 for b is equal to 1 and 0 otherwise. So for the first part, what we have to find is what is the probability model for random variables a and b. Write the joint PMF p of a comma b as a table. So just off the bat, the joint PMF p of ab will be equal to p of b given a into p of a, which is also equal to p of a given b into p of b. But since what we have is p of b given a, that's what we're going to work with. And this is basically theorem 4.22, which essentially states the same thing, that the joint PMF p of x comma y is equal to p of x given y into p of y, which is also equal to p of y given x into p of x. So this is what our table will look like. P of a comma b, and b assumes two values 0 and 1, and a assumes two values -1 and 1. So basically the first entry in the table, which is p of a comma b, where a is equal to -1 and b is equal to 0, is basically P of B given A, B is equal to 0, A is equal to -1 into P of A is equal to -1, and basically P of A comma B for A is equal to -1, B is equal to 1 is P of B given A, B is equal to 1, A is equal to -1, and into P of A is equal to -1, and basically so on and so forth. So basically, the values of these were given in the question itself, and this is direct enough, I suppose. So for the first entry of the table, we have P of B given A, B is equal to 0, A is equal to -1, which is basically the first entry in the second table, and the value of which is 1 by 3, multiplied by PA of -1, which is the first entry of the first definition, which is 1 by 3. So for the first entry, we have 1 by 3 into 1 by 3. And for the second entry, what we have is P of B given A, B is equal to 1, A is equal to -1 into PA of A is equal to -1. So again, for this, we have B is equal to 1, A is equal to -1. So again, we'll be referring to the second definition, where we have P of B is equal to 1, A is equal to -1 is equal to 2 by 3, and PA of -1 is again equal to 1 by 3. So this is basically equal to 2 by 3 into 1 by 3. And for basically the third entry, P of AB for A is equal to 1 and B is equal to 0 is equal to P of B given A, B is equal to 0, A is equal to 1 into PA of 1. So for this, we'll be moving to the third definition, where we have P of B given A, B is equal to 0, A is equal to 1, and the probability of that is basically 1 by 2 into probability that A is equal to 1, which is 2 by 3. So this term is basically 1 by 2 into 2 by 3, and the final term is P of B given A, B is equal to 1, A is equal to 1, multiplied by PA, A is equal to 1, which will basically again be 1 by 2 into 2 by 3. So here we have obtained the table. The final values will look something like this. I hope that's okay with everybody. So, okay. So for the next part, we are given if A is equal to 1, what is the conditional expected value E of B given A is equal to 1? So here applying the standard formula for expected conditional expected value E of B given A is equal to 1 will be equal to the summation of B into the PMF of B given A, B given that A is equal to 1. So for this, we know that B assumes only two values, 0 and 1. So for this, we'll basically have one term in which B will be equal to 0. So that entire term will be equal to 0. And the second term will be where B is equal to 1. And that will be the only non-zero term, which will basically be equal to 1 into P of B given A. B is equal to 1 and A is equal to 1. So this is basically in the third table, and the value of this is basically 1 by 2. So final answer that we have is 1 into 1 by 2. So for the next part, if B is equal to 1, what is the conditional PMF P of A given B, A given B is equal to 1? So so far so given in the question we only have P of B given A. We don't really have the value of P of A given B, but we can find that. So in the first part, we found the joint PMF, which is P of A comma B, and basically to find P of A given B, that will be equal to the joint PMF P of A comma B divided by P of B. So basically P of A given B, A given B is equal to 1 will be equal to the joint PMF of A and B, P of A comma B, A comma B is equal to 1 divided by P of B, given that B is equal to 1. So the joint PMF we have already found in the first part, and now we basically have to find PMF of B, and the PMF of B can be found using the probability definitions that were given in the question. This is basically if you think of theorem of total probability, then B of B will be equal to basically the summation over all possible values of A P of B given A into P of A, right? So if we expand it and write it, since there are only two values of A, this will basically be equal to P of B given A. B given A is equal to -1 multiplied by PA of -1 plus P of B given A. B given A is equal to 1 multiplied by PA of 1. So all these values were given in the question, and we have basically, so, and we need to find this for all possible values of B, which are essentially 0 and 1. So PB of 0 will be P of B given A, 0 given -1, which is essentially the first value from the second table, 1 by 3, into PA of -1, which is again 1 by 3, plus P of B given A, 0 given 1, which is essentially the first value in the third probability definition, which is 1 by 2, into PA of 1, which is 2 by 3. So the value that we get for PB of 0 is essentially 4 by 9. And since there are only two possible values that the random variable B assumes, which are 0 and 1, then the probability PB of 1 will essentially be equal to 1 minus PB of 0, which will be equal to 1 minus 4 by 9, which is essentially 5 by 9. So now that we have found PB as well, what we need to find is basically, all that is left to find is basically P of A given B, right? So this is the complete definition of P of B, and basically P of A given B, A given B is equal to 1 is basically P of A given B, A comma 1 divided by PB of 1. So again, for this we'll refer to the table that we found out in the first part. This part basically says P of A comma B, A comma 1. So these are basically the entries of the second column. So basically we have P of A comma B for values where B is equal to 1. So which is equal to 2 by 9 if A is equal to -1, and 1 by 3 if A is equal to 1, which has to be, so basically 2 by 9 and 1 by 3 are the values for A is equal to -1 and 1. And so basically for A is equal to -1, what we have is 2 by 9 divided by 5 by 9, which is 2 by 5. And for A is equal to 1, we have basically 1 by 3 divided by 5 by 9, which is equal to 3 by 5. So here we have the value of P of A given B, which is what we had to find in this part. So for D part, if B is equal to 1, what is the conditional variance of A given B is equal to 1 of A? So in the previous part, we had just found the probability distribution of P of A given B, A given that B is equal to 1, and finding variance is simple enough. After that, we first have to find the conditional expected value of A given B is equal to 1, which is essentially A into the PMF of A given B, A given that B is equal to 1, which is basically -1 into 2 by 5 plus 1 into 3 by 5. And then we have to find E of A square given B is equal to 1, which will be the summation of A square into the conditional PMF P of A given B, which will turn out to be -1 ka square into 2 by 5 plus 1 ka square into 3 by 5, which turns out to be 1. And variance of A given B, as we know, is basically the expected value of A square given B minus the expected value of A ka whole square, which is essentially 1 minus 1 by 5 ka square, which comes out to be 24 by 25. So this is direct enough. I hope this should be okay with everybody. So for the next part, we have to find the covariance of A and B. So the covariance of A and B is defined as the expected value of AB minus the expected value of A into the expected value of B. So this is also, I guess, convenient enough to find. We already have the probability distributions for A and B. We've found the probability distribution of A was given in the question, and we've already evaluated the probability distribution for B in another part. So the expected value of A will be essentially A into PA of A, which is minus 1 into 1 by 3 plus 1 into 2 by 3, which comes out to be 1 by 3. And the expected value of B will be B into PB of B for all values of B, which is essentially 0 into 4 by 9 plus 1 into 5 by 9, which totals 5 by 9. And basically the expected value of AB will be AB into the joint PMF P of AB, and basically the summation is taken over all possible values of A and B. So this will essentially come out to be 4 terms, but among the 4 terms, 2 of them will have B is equal to 0, so those terms will be 0, and so eventually the only terms that we care about are where B is equal to 1. So A is equal to minus 1, B is equal to 1, and multiplied by PAB of A comma B. So you can refer to the table derived in part A for that again. The value for that is 2 by 9, which is basically the second term in the given 4 terms beneath. And basically the last term, which is A is equal to 1, B is equal to 1, and the joint PMF for this is basically 1 by 3, as we have found in part A of this question. So finally the expected value of AB comes out to be 1 by 9, and the covariance of A and B comes out to be 1 by 9 minus 1 by 3 into 5 by 9, which is basically minus 2 by 27. So let's move on to the next question, which is question 4.9.8, which says for random variables A and B given in problem 4.9.7, let the random variable U is equal to expected value of B given A. Find the PMF PU of U. What is the expected value of U, which is equal to expected value of B given A. So from the previous part we have the probability definition of PA, P of B given A, and basically U is equal to expected value of B given A, and we're supposed to find the PMF of U. So first I guess we'll work on finding the expected value of B given A, and A assumes two values which are 1 and minus 1. So what we have here is basically E of B given A is equal to minus 1, and E of B given A is equal to 1. So for both these the formula are quite direct, and I think we've used this in several of the previous questions, and this will basically be equal to the summation over all possible values of B, B into the conditional PMF P of B given A, B given that A is equal to minus 1, which will basically be equal to 0 into 1 by 3 plus 1 into 2 by 3. And for the second part of this we have E of B given that A is equal to 1, which again will be the summation over all possible values of B, B into PMF of B given A, with basically B given that A is equal to 1, which again will be 0 into half plus 1 into half as given in the second probability definition. So what we basically found here are the values of E of B given A, and which is essentially a function of the random variable A, and it assumes the values 2 by 3 for A is equal to minus 1 and 1 by 2 for A is equal to 1, and this is the same as the random variable U, right? So basically U assumes the value 2 by 3 when A is equal to minus 1, and U assumes the value 1 by 2 when A is equal to 1. So essentially the probability that P is equal to 2 by 3, that U is equal to 2 by 3 is the same as the probability that A is equal to minus 1, which as given in the previous question is 1 by 3, and the probability that U is equal to half is the same as the probability that A is equal to 1, which as given in the first question, in the previous question, is basically 2 by 3. So here we have found out the PMF of U, which is 2 by 3 for U is equal to half, and 1 by 3 for U is equal to 2 by 3. Right, so let's move forward to the next question, which is problem 4.10.2, which says x and y are independent identically distributed random variables with PMF Px of k is equal to py of k, which is equal to 3 by 4 for k is equal to 0, 1 by 4 for k is equal to 20, and 0 otherwise. And we have to find the following quantities, which are expectation of x, variance of x, expectation of x plus y, variance of x plus y, and expectation of xy into 2 raised to the power xy. So the first four parts are basically, I think, pretty direct. Only the fifth part may be slightly confusing. So for the first part, basically, to find the expectation of x, we're already given the PMF of x. We just have to apply the formula, which is sigma xpx, which is basically 0 into 3 by 4 plus 20 into 1 by 4, which comes out to be 5. And to find the variance of x, we can apply the formula, basically expectation of x minus mu x ka square. So x minus mu x ka square for k is equal to 0 is for x is equal to 0 is basically 0 minus 5 ka whole square into px, which is 3 by 4, plus 20 minus 5 ka whole square into px, which is equal to 1 by 4. So this comes out to be 75. So next we have to find the expectation of x plus y and variance of x plus y. So since x and y are independent and identically distributed, first of all, the expectation of a plus b and variance of a plus b turn out to be expectation of a plus expectation of b, and variance of a plus b is variance of a plus variance of b. And since a and b are the same here, we basically have e of x plus y is equal to 2 times e of x, which is 2 into 5, 10. And variance of x plus y is equal to 2 times variance of x, which is equal to 2 into 75, which is equal to 150. And for the fifth part, we have basically expectation of xy into 2 raised to the power xy. So for this, we basically have to use the formula again. E of anything is basically that thing multiplied by the probability with which its different values occur. So here we'll have xy into 2 raised to the power xy into the joint probability of x and y, and the summation over all possible values of x and y. So again, this will be 4 terms, but 3 of them will be 0 because either x or y is 0, and only one term will be non-zero where both x and y are equal to 20. So we have 20 into 20 into 2 raised to the power 20 into 20 into basically the joint probability that p of x comma y, and x is equal to 20 and y is equal to 20. Now since basically x and y are independent, the joint probability is basically the product of their individual probabilities, which comes out to be px of 20 into py of 20. And so this is basically a huge number, and on calculating this comes out to be 2.75 into 10 raised to the power 12. Right, so let's move forward to the next question, which is problem 4.10.7, which says x and y are independent random variables with PDFs fx of x equal to 1 by 3 e to the power minus x by 3 for x greater than equal to 0 and 0 otherwise, and fy of y, which is equal to 1 by 2 e to the power minus y by 2 for y greater than equal to 0 and 0 otherwise. And in the first part, we have to find what is p of x greater than y. In the second part, we have to find what is expected value of xy. And in the third part, we have to find what is the covariance between x and y. So the first thing that one would notice is that x and y are both basically exponential random variables. X has the parameter lambda equal to 1 by 3, and y has the parameter lambda equal to 1 by 2. So this information might be useful later. So let's proceed with the first part, in which we basically have to find the probability that x is greater than y. So to find this, we'll basically revisit theorem 4.7, which says that the probability that the continuous random variables x and y are in A, where A is a region, is given by P of A is equal to the joint PDF fxy dx dy over the region A. And so for our problem, the region A is defined as the region where x is greater than y. So the probability that x is greater than y is basically the double integral of the joint PDF f of xy dx dy over the region A, which is x greater than y. Now, since x and y are independent, their joint PDF will basically be the product of the individual PDFs, which is fx comma y is equal to fx into fy. So basically integrating over the area. So basically the limits of x will be y to infinity, and the limits of y will be 0 to infinity, as basically that is the region where y is defined on 0 to infinity. And so yeah, basically what we get for the integral is 1 by 2 e to the power minus y by 2 into integral of 1 by 3 e to the power minus x by 3 dx, and the limits are from y to infinity. Now, you should notice that the two integrals cannot be separated, because when integrating over the region of x, one of the terms is y. So these two integrals are not basically independent. And so basically on simplification of the term, we get 1 by 2 e to the power minus y by 2 into e to the power minus y by 3 dy. And you can do the math on integrating and putting in the limits. You will basically get the value 3 by 7. So for the next part, we have to find the expected value of xy. And so we just stated that x and y are both exponential random variables, and using integration by parts, we can find the expected value of an exponential random variable, which basically comes out to be 1 by lambda. Now lambda for x is basically 1 by 3, and lambda for y is 1 by 2. So basically the expected value of x comes out to be 1 upon 1 by 3, which is 3, and the expected value for y comes out to be 1 upon 1 by 2, which is 2. And now since basically x and y are independent, their correlation comes out to be e of xy, which is equal to e of x into e of y, and which is basically 3 into 2, which is equal to 6. So for the third part, we have to find the covariance of xy, and we just found the value of e of xy, which is basically 6 minus mu x mu y, and which is basically the same again. And so basically for independent random variables, the covariance between two independent random variables is always 0. So moving forward to the next question, we have x1 and x2 are independent identically distributed random variables with expected value ex and variance of x, and we have to find what is e of x1 minus x2 and what is variance of x1 minus x2. So this question is quite easy. So e of x1 minus x2 will be, since these are independent random variables, you can just go ahead and separate the terms without thinking much. So e of x1 minus x2 will be e of x1 plus e of minus x2, and e of minus x is basically the same as e of minus x. So this will come out to be e of x1 minus e of x2, and since x1 and x2 are identically distributed, this comes out to be 0. And for variance of x1 minus x2, basically the first thing to note is that variance of minus x is not equal to minus of variance of x, but in fact is equal to variance of x. So variance of x1 minus x2 will be equal to variance of x1 plus variance of minus x2, which will come out to be 2 times variance of x instead of becoming 0. So